Yes, thank you very much. So my plan for today is to report on some recent progress on the inner model program, and in particular outline why universally Baire sets are important for inner model theory, but at the same time also sort of problematic. So I will go into the details of this claim during my talk. Let me just jump right in and start with the definition of universally Baire sets. So being universally Baire can be seen as just a generalization of being Suslin. So, I mean, looking at the audience, most of you should have seen that a Suslin set is just a set that's the projection of a tree. Yeah, so we say a set of, let's say A. Suslin, if it's of the form A, is the projection of a tree T, and T is some tree on omega times kappa for some large ordinal kappa. And being universally Baire just means being the projection of a very nice tree. Let me formalize what a very nice tree is. So for a pair of trees S and T, we say that the pair S and T is absolutely complementing, or Z absolutely complementing for some fixed set Z, if the projection of S is the complement of the projection of T, but not only in V, in any generic extension of the universe, and in this case, in any col omega Z generic extension. And we say a set of reals is universally Baire if it's sort of given by such a complementing pair of trees. So this was introduced by Feng, Grigor, and Woodin, and they showed that, I mean, they actually proved that their definition is equivalent to the following. So for every set Z, there are Z absolutely complementing trees, S and T, such that A is the projection of S in V. And what's so nice about this definition is that it allows us to extend the definition of A onto generic extensions. And this is really the key property. And actually, if you take some care, you can sort of formulate it as another equivalence to being universally Baire. So the idea is if we take our set theoretic universe, V, and let's say we have our set A somewhere in here. So it's a set of reals. And we go to some forcing extension. Let's say again, this is V. Now we go to an extension, V of G. I mean, of course, we still have the old set A, but maybe this is not really the way we would like to think of A in the forcing extension. So maybe this should really, I mean, the collection of these sets should really what A is in the generic extension, and the fact that A is universally Baire allows us to really make sense of this. Yeah? If A is universally Baire, A is the projection of, I think I call it S here, some tree S in V, and now we can just in V of G define that the canonical expansion of A is also the projection of the tree S, but now in the generic extension in V of G. And this is really the key idea behind universally Baire sets. This is what makes them really useful. But they come from topology, actually. So an equivalent definition that's sort of due to Schilling and Ward, at least Grigor claims that all the time, but it's not really written in their paper. But this was sort of maybe the inspiration for Feng, Grigor, and Woodin. So the original definition is that a subset of a topological space is universally Baire if it has the property of Baire in any continuous preimage. So, I mean, this explains why it's called universally Baire. Yeah, but I mean, the way we want to think of it sort of from the inner model theoretic perspective is really like this, because the nice thing is, I mean, we now have a property, for example, in the iteration strategy or for mice or some other property you would like. And we have that property for the reals in V. But now we want to extend it to larger ordinals, for example, or larger cardinals. Yeah, I mean, we know we can say something about the reals. For example, we can iterate a mouse for countably many steps, but now we want to extend it and we want to do this for, I don't know, omega-3 many steps or even more. Yeah? How do we do it? Well, we can just look at the extension where we collapse that cardinal. So now we have more reals. And then actually the question we were asking about omega-3 becomes a question about the reals. And we can extend our strategy or other property, whatever we like, our set A, onto the generic extension, and we get a very canonical definition of what the strategy or the property or whatever should be in the Dinac extension, where the things we were interested in, the larger object we were interested in, actually turn out to be just reals. And this is why these universally Baire sets are sort of important, and they show up everywhere in our model theory. And the point is, I mean, how is this connected to the notions that we already know? For example, I mean, an old result by Martin, Seal, and Woodin shows that if there are two Woodin cardinals, then every universally Baire set is determined. I mean, universally Baire sets, they all have regularity properties. For example, they're very natural in some sense. And in fact, Ita and Neyman showed that you can do this from one Woodin cardinal, just if you want to optimize the hypothesis. But at the same time, under the axiom of choice, not every set of reals is universally Baire, because they do have the regularity properties. So the question is, how do the universally Baire sets look like, for example, in a model of determinacy? Can we actually get a model where all sets of reals are universally Baire, sort of the ultimate canonical model for universally Baire sets? Well, I mean, this question was answered by Grigor Sargsyan together with Paul Larson and Trevor Wilson. So they showed from large cardinals, actually, if there is a cardinal lambda, that is a limit of Woodin cardinals and a limit of fully strong cardinals, you can do sort of a derived model construction, and you get a model of the axiom of determinacy where all sets of reals are universally Baire. And of course, the most natural question to ask, and it was conjectured by Grigor, that this is optimal. Yeah, can we reduce the large cardinal strength, or is this really the exact level? Yeah, so on the one hand side, we have a determinacy statement, and we have a large cardinal statement on the other side. And as you might have heard, in our model theory, we always ask the question whether we can actually combine the two. So this is one implication. The question is, can we go the other way around? It turns out that this is actually the case. So I proved sort of last year that what Grigor conjectured is true, and the statement was indeed optimal. So if there's a model of AD where all sets of reals are universally Baire, we can get exactly the right large cardinal hypothesis back. So we get a cardinal lambda that is a limit of Woodin cardinals, and at the same time a limit of fully strong cardinals. And I mean, the proof of this is actually very technical because it goes through so-called hybrid mice and a translation procedure that translates iteration strategies into these strong cardinals. But this already uses the fact that we talk, I mean, the iteration strategies we consider there are universally Baire. I mean, we start from a model where all sets of reals are universally Baire. So in particular, the iteration strategies we look at, for example, the objects that we want to translate are universally Baire. And this plays a crucial role in the proof of this as well. So let me speak more generally for a moment, yeah? I mean, what is my vision or other people's vision behind these ideas? I mean, why do we study these properties? Well, this connection we have between determinacy and large cardinal axioms should continue throughout the large cardinal hierarchy. Yeah, I mean, it started at analytic determinacy and measurable cardinals by Harrington and Martin, and it was extended in the 80s by Martin and Steele and also Woodin to higher levels, for example, projective determinacy and Woodin cardinals and determinacy in L of R and so forth. And we have many more results. And in some sense, what I just showed you is also one result along these lines. But I mean, philosophically, for me, there's no reason why this should stop at some point. I mean, these connections are so canonical. I mean, we should be able to extend them. And I mean, ultimately, we should be able to extend them just step by step to, for example, get the exact consistency strength of the proper forcing axiom. But we are not there yet, yeah? And the question is why? So where's the problem? Currently, the main barrier we are facing is at what's called the Woodin limit of Woodin cardinals.
One step up.
Well,
Fifth one.
You can continue the picture infinitely. Yeah?
Oh, I think here's the other guy.
But I mean, what you can see, I mean, why I like this cartoon is because, I mean, the way this is done, I mean, one guy is walking up here. I mean, this is maybe the guy who is proving that you can actually get PFA from whatever, I mean, from PFA you get a Woodin limit of Woodins. But it's not possible to do that without the support of the community, yeah, because this is a project, I think, that the whole community will solve. It's not a one-person project. Yeah? And so you need a second person who will, for example, develop the tools that allow you to walk up the staircase. Yeah? But anyway, I mean, we do have a barrier at the moment. And I mean, there are actually several ways to say why this is a barrier. And I will just pick one which is related to sealing. And I mean, actually, I'm not sure. Maybe Grigor will talk about the other one. I don't know. But there are various ways of like formulating why the Woodin limit of Woodin cardinals is a barrier currently. Okay, so as I said, one way is given by sealing. So what is sealing? It's just an ultimate extension of Schoenfield's absoluteness theorem in some sense, the generic absoluteness statement. So Schoenfield's absoluteness theorem, like in a baby version, states that sigma and two facts cannot be changed by forcing. Yeah, it's more general, but one consequence is that in forcing extensions, sigma and two statements always remain the same. And there's an extension of this, that's a theorem by Woodin, that allows you to preserve the theory of sort of one universally Baire set. Let me go through this more slowly. So if A is universally Baire set, just one fixed universally Baire set, and let's say there's a class of Woodin cardinals, then the theory of L of A, R cannot be changed by forcing. So what do I mean by this? So you take the universally Baire set and you take the reals, and you look at everything that's constructible over these objects. And you can look at the theory of that model. Yeah, so these are a lot of statements. This is much more complicated than just sigma and two statements. And you can think of this as a point class, a complexity class. Yeah? And in this sense, it's a very complex one. But Woodin proved that whenever you have two set generic extensions, one extending the other of the universe, so VFG and VFG star H, there is in fact an elementary embedding that maps L of A, so L of AG, RG, and now AG is just the canonical interpretation, just like here, of the universally Baire set in the generic extension, and RG are just the reals of VFG. So this is the canonical interpretation of L of AR in the generic extension VFG. And so there's an elementary embedding between this and the canonical interpretation of L of AR in VFG star H. And the fact that there's an elementary embedding means that no new statements can be true about anything in that model. Okay, so this is a way of stating a generic absoluteness theorem. And sealing is essentially the same thing, but much stronger. The sealing is similar, but instead of just putting a single universally Baire set there, we put the class of all universally Baire sets, the collection of all of them. And we ask, can we get a similar statement? Can we say that the theory of all the universally Baire sets together with the reals does not change if we go to a forcing extension? So let me give you the formal statement. So the first statement is just sort of a structural property that tells us that the models we are talking about is nice. So let me just write the notation to be sure that you remember. So here, RG is really just the set of reals in VFG, and gamma infinity G is just the collection of all the universally Baire sets in VFG.
Yeah.
I mean, not the trees, the projection of the trees, but in VFG. So, I mean, every set that's universally Baire in VFG. So if in VFG you find a pair of absolutely complementary trees, the projection of one of them is going to be universally Baire, and you take the collection of all of these. I mean, if you take the trees, you sort of pick the weaknesses. But I mean, technically what I mean is really the sets of reals that are universally Baire.
So, but then the tree might not be in the model. So
I mean, the tree has to be in the model. I mean, when I say universally Baire sets in VFG, I mean that the pair of trees is in VFG, and we look at the projection of S in VFG.
I guess could you have two different witnessing pairs and maybe only one of them is in the model or something?
It doesn't matter. As long as there's one, that's perfectly fine. I mean, I just look at the model, just like if you would like look at B, And they say, okay, what are the universally bare sets in that model? So these are given by trees that are in the model. And we just ask, yeah, what this set is sort of, yeah. And I mean, the first statement just says that, okay, if we build this model where we construct over the set of all universally bare sets now and the reals, then this is a model of determinacy, in fact of 80 plus, so technical strengthening of determinacy. And in addition, this model has a nice closure property. So actually the set of reals in that model is all the universally bare sets. So sort of, I mean, if you think about the model, if you consider it sets of reals, universally bare sets are all we need to care about. And then if we have these structural properties, so the first one is really sort of a technical assumption. It's not the key property. The key property that makes the strongest the second one, which looks like exactly like the theorem in the statement of Woodin's theorem I had on the previous slide. So we now say for every set generic extensions, V of G, and then further extension V of G star H, there is an elementary embedding that maps L of the UB sets of V of G and the reals of V of G to L of the UB sets in V of G star H and the reals of V of G star H. And now we have one more requirement. We want to make sure that the UB sets get mapped correctly. So if we take a UB set A in gamma G infinity, then we map it to its canonical expansion in the further generic extension. The J of A is just A sub H. And the question is this true? Does it hold? Does it follow from a large cardinal? Is there a counterexample in certain cases? Yeah, what is the strength of this statement? So before I go into this, I want to give you one brief slide on why we actually care about it. Yeah. So the following is a test question for the inner model program. Is there a large cardinal that implies sealing? Why? Well, short answer, if yes, then we really need to rethink the way we think of inner models currently. So why is this the case? I mean, let me give you sort of the heuristic idea behind this. So I said universally bare sets appear everywhere in inner model theory. For example, all the canonical models you construct, they have universally bare strategies. In fact, the power set operation sort of in these models is universally bare in some sense. So the models, I mean, you can make sense of this more formally, but in some sense, these models are all universally bare. This is the way we construct them. Okay, what sealing tells us now, if sealing is true, then there's no way of constructing more complicated universally bare sets, because the theory of the universally bare sets is frozen. So it means that there is a bound on how complex we can get with considering universally bare sets. So if there's a large cardinal that implies sealing, for this large cardinal and beyond, we cannot construct the inner models the way we do at the moment. So this is a crucial question. And maybe you just want to hope that sealing is very strong, and so we don't have a problem. Yeah, but it's an important question that we should find an answer. Yeah, if there is a large cardinal that implies sealing, or if sealing holds, for example, in a forcing extension of a very small large cardinal, or whatever small means. I mean, not a measurable cardinal, yeah, but something between a measurable and a supercompact. But I mean, we want to determine how strong the statement is. And if we, for example, can get sealing in a mouse, we find a canonical inner model that satisfies sealing. This is sort of the bound where our canonical models have to stop. So, I mean, being constructed the way they're constructed at the moment. So what do we know? How strong is this statement? So Woodin proved somewhere probably in the late 90s or early 2000s that sealing is consistent from a supercompact cardinal in the proper class of Woodin cardinals. So if you take a proper class of Woodins and some supercompact and you collapse 2 to the kappa for the supercompact cardinal, then sealing holds in the forcing extension. And this is a stationary tower forcing proof. More recently, Grigor, Sargsyan, and Trang sort of gave us a really big warning. Yeah? They proved that the consistency strength of sealing is well below that. So they showed that if there's a Woodin limit of Woodin cardinals, then sealing is consistent. And so this is why a Woodin limit of Woodins might be really a main barrier here. Yeah? I mean, this does not prove that sealing holds just in a model with a Woodin limit of Woodins, but it's a warning. Yeah? It's a warning that we should look further and we should try to optimize Woodin's result and maybe get it from a smaller large cardinal hypothesis. And they proved even more. They also proved that if you have a proper class of Woodin cardinals and a strong cardinal and so-called self-iterability, so if you assume that the universe is iterable and it can see that, then also sealing holds in a forcing extension. So the sealing holds after collapsing the successor of the least strong cardinal to be countable. Again, this is a warning because this is also something that has sort of lower consistency strength. It's, for example, you can get such a model from a Woodin limit of Woodins, but it does not hold in a mouse because mice don't know how to iterate themselves. The self-iterability is something that, again, it's a canonical property, and this should make us think, and this is a warning, but it doesn't imply directly that the way we construct inner models at the moment will not extend, yeah, but it makes it kind of likely. So how do we try to improve Woodin's theorem? Also, what we did is we found a new proof of his theorem, and hopefully this will inspire us to also lower the large cardinal hypothesis. So recently, together with Grigor, Sargsyan, and also Bartosz, Wcisło, we found a new stationary tower free proof of Woodin's Sealing Theorem, building on ideas of Grigor, Sargsyan, and Trang and the self-iterability result. And let me just state the theorem formally. So this is Woodin's Sealing Theorem, and it's exactly the same statement that we proved. So let kappa be a supercompact cardinal and let G be collapsing 2 to the kappa to be countable. Then if there's a proper class of Woodin cardinals, we get sealing in the generic extension, P of G. And in fact, I want to give you some key ideas of the proof together with Grigor and Bartosz. And what makes the proof really interesting for me is that it's something that people could have proved in the 80s, actually. There's one technique that was developed a little bit later, that's Niemann's genericity iterations. But everything else is just universally Baire sets, homogeneously Sussman sets, and so-called flipping functions. They're the whole argument does not use any deep inner model theoretic machinery. If you give me maybe 3 hours, I could actually give you the proof on the board, and there's there's really no deep inner model theoretic machinery. There's no inner model. There's no fine structure. There's really nothing that makes you worry maybe that you wouldn't understand the argument. Yeah, it's really very elementary, and this is what I think makes it really nice. Yeah, and this is why for me it feels like this is the right way to prove the theorem. But still, okay. How do we do it? We need to analyze this model. We want to find an elementary embedding between this model L, gamma G infinity and RG, and the same model of the further generic extension. Yeah. So maybe let me just write. Write this. So gamma infinity G star H and R. G star H. Yeah, so the key property of sealing is that we want to find an elementary embedding between these two models. How do we do it? We want to find a canonical representation of this model, and the same way also of this model, as a so-called derived model of a direct limit model. So we take some hulls, we iterate but coarsely, yeah, no fine structure, just like Martin and Steele did it in the 80s. And we obtain a direct limit model, and sort of in the direct limit, we look at a canonical collapse, Levi collapse, and this allows us to sort of obtain the same model in a more canonical way. And this representation allows us to find the elementary embedding. And the way how to find the elementary embedding from the derived model representation is what Grigor and Nam already did in the self-iterability argument. So what's new is how to get this direct limit model. And what we did is we invented a new technique of making universally Baire sets generic. So you can, most of you probably have seen that if you just take the countable substructure of the universe, you can take a real that's external and you can iterate the model to make the real generic. And there's Woodin's extender algebra, and there's also what I just mentioned, Niemann's genericity iteration, that allows you to do this with less iterability. And I mean, we need to use that, so we make the reals generic, but at the same time, we want to make the universally Baire sets generic. So we take a universally Baire set in V or V of G, and we want to make it generic over a small substructure. So we iterate the structure, and we want to make sure that in the generic extension of the iterate, I mean, not only the set exists, but we can see that it's universally Baire. So we are sort of making the homogeneity system generic that witnesses that this given set is universally Baire. And this is not all. I mean, the second ingredient we need, once we see the universally Baire set in the iterate, we need to make sure that it sort of stays universally Baire in further iterates. And we even want to be able to take a sort of very long extender that overlaps the whole picture and make sure that in the ultrapower, it stays universally Baire. I mean, so not only the set stays there, but it stays there as a universally Baire set. So we have measures and homogeneity systems and so forth. And I mean, it turns out that actually this property seems to be rather complicated. So I mean, we abstracted sort of a large cardinal property, if you want to think of it like this, that tells you that universally Baire sets that are given sort of like this are preserved onto further ultrapowers. But I mean, we can, for example, prove that this is, this property follows from a supercompact cardinal. I believe it should be something less here, but it's not a very weak property in the large cardinal sense, I think. And if you put all of these sort of elementary techniques together, you can get Woodin's Sealing Theorem. And I mean, the idea behind this is, of course, I mean, first that maybe by refining the argument, we might be able to reduce the large cardinal strength, but also the way the argument is set up, it most likely will allow us to also prove other properties in the model. For example, in addition to sealing, get something like theta regular to just push up the strength of the model we get. So let me finish by summarizing the main issues here. Yeah. So I mean, we've seen that there's this connection between determinacy and inner models, and also these hybrid mice that I briefly mentioned, so mice that can sort of iterate themselves, have strategies. And I mean, in the past years, it has been shown by many people that these connections have actually applications. I mean, in finding the consistency strength of PFA, but also in general topology, model theory, and many other areas. And I believe that if we can keep extending this connection, we will find more and more applications. And this is like the backbone of what we do in inner model theory and also more generally in set theory. So this connection is expected to continue, but currently we have this barrier at the Woodin limit of Woodins. But universally Baire sets and sealing are one key property that we should study to get a clear picture of the universe at this level. And so let me leave you with the big open question here. Is there a large cardinal that implies sealing? And I mean, I really hope that we will answer this in the next years, because it would really shed light on how the inner model program should continue. Thank you.